So this is a joint work with Hawthorne and Paul that we had recently. The title of the presentation is Distributed Algorithms for Actively Dynamic Networks. So let me begin. So what is a dynamic network? A general description is we have a network whose structure can or may change. We usually represent this by having a graph like this. And what makes it dynamic is that edges may come and go as they please usually. So edges may change or nodes may disappear like that, like I showed in this picture. We can make distinctions between dynamic networks based on, well, their dynamics. We say that they can be either active or passive. By that, I mean that a passive dynamic network is one where edge and node appearances and disappearances are controlled by an external force, for example, by an adversary. While active means that we control the edges and the nodes by using an algorithm or something else. Another distinction is that we can either have a distributed or centralized setting. Centralized means that we have complete control over the system and we can force every node to do whatever we want, and we usually have complete information, while distributed means that every node acts independently with some kind of local information. And in this talk, we are interested in active and distributed dynamics. So we want nodes to be able to activate connections to new neighbors or deactivate some connections. And we have no central coordinator for the nodes. And our general goal is to take an initial network and transform it into a target network that belongs from a family of target networks. And we do that because we want to exploit some good property that a target network has in order to more efficiently solve a distributed task. So instead of going straight away for the distributed task, we use this transformation to make it more efficient. So here I have some related systems, obviously temporal graphs, population protocols. I'm not going to stay here because the presentation is quite long. I don't have time. I only just wanted to say that the most similar model that exists based on our work is the overlay networks, but even this one has some minor / major modifications that make it different. So let me go to the model. We assume that we have an initial network like this one here on the right. We have a static set of nodes, so the nodes will never change, but we have a dynamic set of active edges, which may change like I show here. We use a standard synchronous message passing model for communication between the nodes. And we assume that every node has a unique ID, 6, 15, 3, and 20, like this. Nodes are only allowed to compare those ID between them. So we are only using comparison-based algorithms. We don't allow more complex operations like addition or multiplication. And as far as the edges go, we say that one node, for example, 6 here, is allowed to activate an edge with node 20 if they share a common neighbor. So since they share 3 as a neighbor, they are allowed to activate an edge. Basically, if they are distance to neighbors, they are allowed to do it. And nodes are allowed to deactivate edges if they are incident to them. And finally, one small remark, there can only be one edge between any 2 nodes. Here I wanted to say that you can assume that there is some kind of underlying graph where that is a click. So all edges exist, but they might be either inactive or active. So what are the problems that we're going to try to solve? We have 3 problems: leader election, where we want to elect a unique leader; token dissemination, where every node has some kind of information that is unique. And we want every piece of information from every node to go to every other node in the system. And that's token dissemination. And finally, we have the depth D tree problem, which is to transform any initial network into some tree, any kind of tree that has depth D. So these are the 3 problems. And in this work, basically, we solve all 3 of them at once by solving the final one. And I'm going to show how that works later on. So we will mainly focus on the final problem while simultaneously basically solving the other 2 as well. So let me start by showing you a small example of how we could solve all 3 of those problems. So assume that we have a ring like this, and we employ the very simple strategy that says every node activates an edge with every distance to neighbor in every round. So we start doing that first with the distance 2 nodes. An example here is This is a distance to neighbor from this node. This is a distance to neighbor from this node as well. So it activates those edges symmetrically for the rest of them as well. Then in the next round, we do the same thing. So if we keep doing that, no matter what the initial network is, after log n rounds, we will always have a spanning click. So if we want to go to any kind of target network, we can just eliminate the extra edges at the end, and we arrive at that. And this is very easy to do even in the distributed way, because in a spanning click, the diameter is 1, so every node can get information from every other node in constant steps. So if I wanted to create a star, I would just eliminate these extra edges here, like this. Okay, so apparently everything can be solved using this strategy. So what is the point of this work? Well, usually activating and maintaining a connection does not come for free in any of the systems that I mentioned before, and in general for graphs. So we have to find a way to quantify that cost. And this is what we do. We introduce 3 measures in order to do that. So the first one is the total edge activations. That means how many edges were activated by our algorithm. Then is the maximum activated edges, which is the maximum number of activations by the algorithm per round over all rounds. And finally, the maximum activated degree, which is the maximum degree of the network based only on the activated edges by the algorithm. By that, I mean that in each round, we check the degree of each node, where we calculate only the edges that are activated by the algorithm. We do that over all nodes, over all rounds, and we take the maximum. So basically, in all 3 of those steps, we do not account for the edges that existed at the initial network. We don't care about those. So here are our results. First of all, we have some bounds only for leader election. So we don't have bounds for the token dissemination or the depth D3 problem. I'm not going to stick a lot in those because I don't have much time. And we have 3 different algorithms that basically try to balance between time complexity and the edge complexity of the measures I introduced before. So there is a clear trade-off between those 2. I'm not going to talk about them right now. I'm going to do it while I'm explaining the algorithms. So before that, I want to say that all 3 algorithms have the same general strategy. That is, we begin by having, or not we begin, during the algorithm, we have all of the nodes being partitioned into committees. A committee is basically a group of nodes that work together. Committees are organized into specific gadget networks that we have, like this one. For example, in our first algorithm, we have a star as a gadget network, and every committee is a star. In the second one, we have a wreath, which is this graph that I have here. I'll explain it later on. So yeah, in each algorithm, we have committees, and every such committee has the structure of such a gadget network. Initially, each node forms its own committee, and it starts competing with neighboring committees, and they merge between them based on some rule that we have. After that keeps happening, we have a final web network that is a single committee. And since it's a single committee that is, for example, a star, we can say that we have solved the depth 1 tree problem, because a star is basically a tree with depth 1. And that is how we solve the depth 3 problem. We have one single committee that has this structure here. Now, we always do that in logarithmic time. And in order to calculate that, what we do is we say that the time that the algorithm takes is based on phases that we have to multiply by the gadget's diameter in order to arrive at the final running time. This may not make much sense right now. It will make more sense later on. So let me start with the first algorithm, which is called graph to star. It takes any initial graph and transforms it into a star in log n time, in big O of log n, actually. So our gadget network is a star. And we use a subroutine here, which is called tree to star. Now, what does tree to star do? Assume that we have an initial oriented tree graph like this one. This is the root. It is a very simple algorithm that basically says every node, since it is oriented and it knows which way the root is, in each round it activates an edge with its grandparent. So this node activates an edge with this one, and then deactivates the edge with its parent. So deactivates this one, like this, for all of them, and deactivation. And then it keeps doing that until at some point it will become a star. And no matter what what initial oriented tree we are given, we can do this in log n time. So this is what we're going to use. Now, I'm going to do this description from a higher level because it is easier to explain. So assume that all of these here I have a network, but these are actually committees. They are not nodes. So each of these committees, if I look at a lower level, they are actually stars. So assume that I have those committees and they have those connections between them. So in every phase, each committee selects the neighboring committee with the highest unique identifier, provided that that ID is higher than its own. So for example, here 7, 8, and 9 will choose 20. Here 13 would choose 16 because it's higher than 14, but 14 would choose no one because the highest UID in its neighborhood is 13, but it's smaller than its own. So if everyone selects someone like this, the arrows I use here to show the selections, I can then partition the graph into basically oriented committees. So since I have some kind of oriented trees here, I can use the tree to star subroutine on committees in order to merge all of the different partitions that I have here. So 7, 8, and 9 will merge with 20, 13 will merge with 16, and everyone in here will merge with 50. And afterwards, the final committees after the merging will inherit the edges that are on the edges of the partitions, like this. So again, I do selection. Here I have only one oriented tree. I execute the tree to star subroutine. I end up with committee 50. And if I go on the lower level, committee 50 will be a star that has all of the previous committees plus extra nodes that those committees may have had. So this is basically how the graph to star algorithm works. So I'm not going to go into detail about the proof because I don't have much time, but I have some kind of proof sketch here. So we say that for any initial connected graph, the graph to star algorithm solves the depth 1 tree problem. That means that we have one final committee that is a star basically. So my proof sketch for that basically says that if you see the graph that I had before, you will see that committees keep selecting neighbors or they get selected by other neighbors. So they keep merging on and on as phases go on. And it is not possible for any committee to stay isolated indefinitely, like committee 14 here, because even if its neighbors do not pick 14 and they pick someone else, after they finish merging at some point, 14 will select the other guy that had a higher ID. And this is why we'll only have one final committee left. Now, as far as time goes, what we use as an argument is that basically in every phase, we use an amortized argument that says that in every phase, every committee doubles its size. So for example, here, after 7, 8, and 9 pick 20, after one phase, if we assume that all committees have the same size, after one phase, committee 20 will absorb 3 other committees of its own, of its size, so it will triple in size. Here it will double in size. Here it will become 7 times larger, but this will require 3 phases of the tree to star algorithm, subroutine that I explained before. So basically, committees almost double in size, And this is why after big O of log n rounds, we will have, big O of log n phases, we will have only one committee left. And and we show that the isolated committees basically only add a constant reduction in the growth that the committees have. Now for the edge complexity, unfortunately, I'm going to omit it, but because I don't have time, the argument basically says that by definition, the algorithm has one edge per node activate per round and one edge deactivate. So that's how we calculate the edge complexity. So for the second algorithm, we said, okay, now this algorithm has the problem that we have a linear degree here because we have a star. Can we sacrifice some of the time in order to improve the degree, the maximum degree of our graph? And this is what we wanted to do. So we created a new gadget that we call Wreath. It looks like this. A Wreath graph is basically 2 subgraphs together. It contains a ring graph, and it also contains a complete binary tree subgraph like this. Assume that this is the root, these two are the first children of the root, and these are the children of the second level, and this is the final child of the third level, and so on if this was bigger. So two subgraphs, a ring and a complete binary tree. Now here you can see that we have log n diameter. So obviously we have improved the linear degree, but we are going to pay it in time because in order for this committee to communicate with itself, it needs an extra log n time that the star graph did not need because the diameter is much larger here. So we use a new subroutine here that is called line to complete binary tree. It takes any initial line and transforms it into a spanning complete binary tree by using the exact same methodology as the tree to star. So you keep activating edges with your grandparents until you reach a point. The only difference is that you have a different stop here. So in order that you don't go to a star, but you finish at a complete binary tree. And we're going to use that for our new algorithm. Okay, so again, the high level from before. The high level of this algorithm is exactly the same as the previous one. There's no difference. Selections are done the same way and merging is done the same way. The only difference is on the lower level because we can't have everyone merging with the leader node of 50 because that would give us the linear degree. So how do we solve that? Okay, let's take this part, the blue partition here. I'm going to go on the lower level. Okay, this is the lower level where every committee is a wreath graph. For simplicity here, assume that all of them are exactly the same and they all of them have clockwise orientation for my explanation. So what we're going to do here is first, we are going to merge all of the rings together, and then we're going to merge all of the complete binary trees together. How do we do that? I'm going to use these two as an example. So this node here activates an edge with a clockwise neighbor of this node. This node activates an edge with a clockwise neighbor of this node, like this. Oh, sorry, my bad. For simplicity, I'm just going to delete here the complete binary tree. So this node, I do the activations that I mentioned before, like this. Then I deactivate those three edges, and you can see that I have managed to merge those two rings together into a single ring. And if I do the same for the whole graph like this, I can go from one ring to a large ring in constant steps. And after that, let's assume that this is the leader node of this committee here. If that node virtually deletes this edge, then now I have a line here, an oriented line that I can use to run the line to complete binary tree subroutine in order to create the complete binary tree subgraph that I also need. So we do that. I haven't drawn it here because it would be hell to do it. So if I do that, I will have managed to merge my committees by keeping the log n degree. So this is basically this improvement of the algorithm. I sacrifice some time because I have log n diameter that I need in order for communication, but I get a much better degree. For the final algorithm, just a few words. It is what it does, it basically says, okay, can we find a middle ground? So both the time complexity here and the degree are in between the values of the first and the second algorithm. So what we do is we use a new gadget network that is a thin wreath. The difference here is that instead of a complete binary tree, we have a complete polylogarithmic tree in order to have a smaller diameter to get better time. We have a new subroutine that only changes what the final tree is. And just wanted to mention that this algorithm requires knowledge of the size of the network for every node, and we have changes both in the low and the high level strategy. So in order to sum up, we have three algorithms that show that there is a clear trade-off between time and degree. So it seems that we can't have both be optimal, but I still have that as an open problem because we are not sure yet. So it might be possible to basically optimize both of them, although I personally am not sure that it can be done. Another open problem would be to change the property of the target network that we want. So here in this whole work, we wanted the target network to have log n diameter. I'm sorry for that. We wanted to have log n diameter because if we have such a small diameter, then we can do leader election token dissemination in sublinear time. And finally, as I showed before in this table here, you can see that there are big gaps on the lower bounds, and we also have no lower bounds for token dissemination and the depth D3 problem. Yeah, and that's basically the presentation. Thank you very much.